And today we're going to do some consequences of it. First one called the open mapping theorem. Open mapping theorem. Okay, and so this is pretty cool. So it says that whenever you have a holomorphic function on a region, as long as the function is non-constant, then the function is an open mapping. Okay. In other words, it maps open sets to open sets. Okay, so let's show this. We want to show that right. So we've got this function on this. We have this function on this open set, and we want to show that that the image is also open. Okay, so we want to show that the image of F is open. So take any point. So let W naught be in the image. Choose some point in the image. We want to show that that guy is interior, right? That W naught is interior. Interior to the image. In other words, that that we can find there's an epsilon neighborhood around it. There's some epsilon neighborhood around it where everybody inside here is in the image. Okay. So we want to show that we hit every there's some. Right, so here's omega. Right. Here's W. It's in the image. We want to show that there's some epsilon neighborhood such that everybody in there is hit by F, right? F covers that thing. Okay. So so W naught is the image of some point F naught, Z naught. Sorry. Okay. Okay. So the proof of this is to say, well, look, let's consider disks. Let's consider circles centered around Z naught. Okay. There's got to be one of if we look at all the circles centered around Z naught, there's got to be one of them that does not hit W naught. That doesn't whose image does not intersect W naught, right? Because if they all did, what would that tell you? Right. Suppose that every circle that you chose around Z naught had a point that mapped to W naught. What would that tell you?
Is W naught a point or a disk?
W naught is a point. So remember,
yeah, if they were all mapped to the same point, then F would be 0. It would be constant.
It'd be constant, equal, yeah. F would be
0.
F would be be constant equaling to W naught, right? Because this would be a limit point. If you looked at the function F minus W naught, right, then that would have its set of zeros would have a limit point, right? Right. Okay. So here's Z naught, here's W naught, right? And we know that there is some circle around there that doesn't hit W naught, right? So we know since F is non-constant, we know that there is some delta such that F of Z is not equal to W naught on the boundary of the disk of radius delta around Z naught. Yes?
And Z naught is in the image of W through F?
Z naught is the point that got mapped to W naught. Sorry, I didn't say that at the beginning. Okay. Okay, so right, so there's some disk that gets mapped. There's some circle here, right, radius delta that gets mapped out here, and it doesn't, hit W0, right? Okay, so it has some image over here. Okay, so right, so there's some one. We know that, so by compactness, there exists some epsilon such that the distance of the image from W0 is always bigger than epsilon. Right? There's a minimum distance from W0 to the image of the circle. Right? Because this is compact. Question? Do you have a question, Kai?
I was going to say, by the compactness of what?
By compactness of the image.
Okay.
Yeah. Right. So like this is a
But that's a
compact
compact
set.
set, so it's mapped to a compact.
It's mapped to a compact set.
Good. Thank you.
Yeah. Okay. So we know that there's some definite distance between W0 and that image. Okay. Okay. So okay. So what's the point? The point is that so there's some. We can take a circle of radius epsilon here. Okay, we can take a circle of radius epsilon here, so that it just barely intersects the image. Okay. Okay. So yeah. So then. For any, so this epsilon neighborhood here is going to be the one that we cover, right? We're trying to show that that we cover that W0 is interior to the image, and we're going to see that epsilon neighborhood is covered by the function. So yeah, so maybe let's go over here. Okay, so pick any W in that epsilon neighborhood. Okay, the distance from W to W0 is smaller than epsilon, of course, right? Right, and also. The distance from f of z to W0 is bigger than epsilon, right? And we have this. Right? Okay. So what does that tell you? By Rouche's theorem, we know that this guy and this guy that these two guys have the same number of zeros, right? Have the same number of zeros inside of that disk. Right. Have the same number of zeros inside of the epsilon neighborhood. Right. Right. And since this has a zero there, then this guy also has a zero there. And so f of z must equal W inside there. Oops, sorry. This should be n delta. right? Right. So it's kind of a funny thing, right? We create this constant function, right? Your g of z is this function, right? Negative w plus w naught, right? So you've got this constant function. You've got this function. You've got this function on the disk, right? And then you've got this constant function on the disk, right? And right. So on the boundary of the disk, you know, this perturbation is always smaller than the function, right? So by Rouche's theorem, when you add them together, the number of zeros is the same. Okay. So the original guy and this guy have the same number of zeros, and so this guy has a 0, and so we do hit W. Okay, everybody okay? Yep. Okay, good. Okay, so some nice corollaries of the open mapping theorem. First is the so-called maximum modulus principle. Okay, so recall that we say f attains a max. At some point, if the size at that point is the biggest possible, right? So. Okay, so maximum modulus principle says that so it says, let me just write it out. Say I have some function that's holomorphic on a region. If f is non-constant, then f cannot attain a maximum. Okay, or in other words, like, if it attains a maximum somewhere, then it must be a constant function, right? Okay, and the proof of this is completely trivial once you have the open mapping theorem, right? You have some point. No matter what happens, if you take any point z naught and you look at its image through f of z naught, right? So z naught is sitting inside of your region omega, right? That cannot be a maximum distance from the origin, right? Because because f is an open map, right? So f is an open map. Take some open disk around z naught. You know that that f of z naught is going to be interior, right? F of z naught is going to be interior, and so there's no way that could have been the maximum modulus. Right? Because you've got a full disk living around. You've got a full disk living around f of z naught. Right? You've definitely got points that are. Right? You've definitely got points that are outside of. Right? If you look at the disk of radius f of z naught, you've got your guaranteed points that are outside of that disk. Right? So you've got points that are bigger than f of z naught in modulus. Okay. So it's very, very easy once you have the open mapping there. a corollary is that, again, if you have a function that's holomorphic on a region, and so if the closure of the region is compact, and f has a continuous extension to that closure, then f on the closure attains its max on the boundary, right? In other words, on the closure, excluding it doesn't attain its maximum in the original region, but on the boundary of that region. The maximum has to occur on the boundary. Right. And the proof of this is equally simple, right? You say, well, you know that it attains a max, right? So f by assumption, f is continuous on this compact set, right? And so you know that it will attain a max somewhere, right? So this thing attains a max somewhere. Right. It attains a max, somewhere on that complex set. Right. But by the maximum modulus principle, you know it can't occur in the region, right? Unless it's constant. Right. Yeah. And in that case, the maximum occurs on the boundary anyway. Right. So by the maximum modulus principle, if the max occurs in omega, then f must be a constant. F must be a constant, and in that case, the max occurs on the boundary, right? So either the max occurs on the boundary, or the function is constant and the max occurs on the boundary. So in either case, the max will occur on the boundary. So in other, you know this by other, so for example, if you had a function and it attained 0 on the boundary, you had a continuous extension to the boundary where it was 0, well then it would have to be 0 everywhere. Okay. Okay. Let's go now for the big theorem in this section. This having to do with homotopies. Homotopies and simply connected domains. Okay, so has anybody taken a course in topology yet? Okay, so you've probably seen this term homotopy. You're probably quite familiar with the term homotopy. Okay, so here's what we're going to use as our definition. Okay, so I'm going to say it in kind of a weird way, but it'll work out. So if there exists a family of curves if there exists a family of curves gamma sub s into some open set. Okay, so you've got this family of curves, right? So and s is going to range from 0 to 1. Okay, so there's gamma 0, right? Here's omega, right? Gamma 0 is you got some curve called gamma 0, right? That right? You have some interval AB. You have a map gamma 0 that creates this curve, which we're also going to call gamma 0. Okay, and you've got curves gamma s from s goes from 0 to 1, right? And then it ends at gamma 1. Okay. Okay, so you have some family of curves such that they have common endpoints. They have common endpoints alpha and beta. Okay, so the picture I've drawn here is not right because they don't have common endpoints. There should be some alpha and some beta, and all the curves should have the same initial point and the same terminal point. Okay, so every curve is going to start at alpha, every curve is going to end at beta, whatever gamma s you choose. Okay. 2, this function here, gamma s t, is jointly continuous for s in 0, 1 and t in a comma b. Okay, so it's continuous in each variable on this on this domain, this product domain. Okay, then we say gamma 0 and gamma 1 are homotopic. So roughly speaking, it means that you can deform one curve into the other curve in a continuous manner. Okay, without within the set omega. So for example, right, if I have a set like this, and I have a curve that is just a simple loop, right, then I can deform that curve. I can deform that curve into a curve that's just a constant point, right? I can shrink that curve down to a single point in a continuous way, right? But if my domain has a hole in it, right? If my domain has a hole in it, and I have this curve, and I look at a simple loop, I can't deform that curve into a constant point because you get caught on the hole, right? You get caught on the hole, right? And in topology, this allows you to distinguish between objects that have holes and objects that don't have holes. Right, so like if you have a torus, like the surface of a donut, right? Then, if you have a loop that goes around the hole in this way, then that curve cannot be deformed to a constant. And similarly, you have a curve that goes around like this, then that curve can also not be deformed to a constant. And so this gives you studying what's called the fundamental group of equivalence classes of these curves gives you a tool with which you can distinguish different topological objects from each other. Okay, so you guys should take a course in topology. It's fun, it's good. Okay, so so we're gonna do the what's called in some books deformation theorem. Okay, so it simply says, and maybe yeah, actually, let me do it over here because we're gonna need some space. So deformation theorem, which says the following, that just that if you have two curves and they're homotopic to each other, then if you have, sorry, I should say, you have a function that's homomorphic in some open set, and you have two curves that are homotopic, then the integral over the curves is the same. Yes?
Is there a way to define homotopy without the language of metric spaces?
Well, you just need you don't need a metric, you need a topology.
Okay.
Yeah, right, because all you need is the notion of continuity.
Okay.
Yeah. I hope. I think so. Okay. Okay. So, right. So this says that whenever you can deform one curve into another, then the integrals are the same. Okay. And yeah. So yeah, the proof of this is a little bit involved, but let's do it. Okay. So okay. So start off with the homotopy. That's this function, which we'll call capital F, on 0, 1 cross AB into your set. Okay. So this is the function that basically encapsulates that deformation from one curve to the other, right? So f of st is going to be defined as gamma sub st, right? So right. So right. So here's a comma b saying 0, 1. Right. Your function maps into your omega, right? And basically, at time 0, that's going to give you your gamma 0, right? That gives you your gamma 0, and then at time 1, it gives you your gamma 1. Right, and in between it gives you the images of gamma s, whatever s is, right? Gamma s. So you've got these curves that slide from one guy to the other guy. Okay, so that's the so-called homotopy. So observe that the image is compact by continuity. Because you're continuous on a compact set. The image is compact. Let's call it K, and so let epsilon be 1/3 of the distance from K to the complement of omega. Okay, so omega complement is out here, and we said this many times before, right? Whenever you have a compact set and you've got this disjoint closed set out here, then there's some minimum distance, right? There's some minimum distance. That distance we'll call 3 epsilon. Okay. So now, by uniform continuity, and this requires a little bit of work, but you can show it. By uniform continuity, there exists a delta such that if S1 and S2 are within delta of each other, right? So in other words, if we take two different times, S1 and S2, so there exists some little delta, so that if these guys, any of these two guys are within delta of each other, then there's some constraint on how far the curves can be from each other. Okay, then the distance between corresponding points, the distance between corresponding points is smaller than epsilon, right? And that's overall, so for all t in AB. Okay. Right. So if I drew this, this is not really the right picture, but you've got one guy and you've got another guy, right? And what it's saying is that so I'm just pretending that these points are on the same at the same time, right? It's saying that these distances, the distances between the corresponding points is smaller than epsilon. Okay, so yeah, so choose, fix any two, S1 and S2, that satisfy that condition, right? So their identifiers are within delta of each other. Okay. And what we're going to show is that we'll show that if you integrate f over S1 and integrate f over S2, the integrals are the same. And so because because we can cover 0, 1, we can go from we can go from gamma 0 to gamma 1 in a finite number of steps, right? And so they're all going to be the same. Yeah.
Like, in order for those integrals to be defined, our intermediate curves have to be smooth. Is it always true that if two smooth curves are homotopically equivalent, then there exists a way to transform one to the other where each of the intermediate curves is smooth?
That's true, but it's definitely true because it's definitely true, and let me find some theorem that will say that's definitely true.
Okay.
So I guess what you're worrying about is that we only assume continuity. Is that the problem?
Right, that in our definition of homotopy equivalence, we only assume continuity for our intermediate gamma s's, and not necessarily holomorphicity, or not holomorphicity, smoothness.
Mm-hmm. Let me see if I can find why it's definitely true.
Okay.
Yeah. Yeah. Okay. Okay, so let me remember what we're doing here. We're trying to show that the integrals of these guys are the same, right? Okay. So here's the trick. You say, okay, so here's gamma S1, and here's say gamma S2. So choose points on gamma S1, Z1 to Zn plus 1. such that the distance between them is always smaller than epsilon. So the distance between zi and zi plus 1 is smaller than epsilon for I equals longer n. Okay. Actually, I think we start from 0. Sorry. From 0 to n plus 1. Okay. And also that z0 is alpha and zn plus 1 is beta. So here's alpha, here's beta, and we choose points that are distance less than epsilon from each other. Okay, so then let wi be the corresponding points. On gamma S2. Okay, right, so each of these guys corresponds to a particular time. They use that same time, right? So, right, if zi is gamma S1 t sub I, then let wi be gamma S of 2 t sub I. Right, so just use the same time. Use the same time for each point. So that of course gives you that the distance between those corresponding points is less than epsilon. Right? That's what we wanted. Okay. So if this point is z sub I, and this point z I plus 1, this point wi, this thing wi plus 1, then it's easy to see that if you take a disk of radius 2 epsilon around z sub I, then that will cover all 4 of those points, right, by the triangle inequality. Because the distance from here to here is epsilon, from here to here is epsilon, from here to here is epsilon, right? So it's possible to create disks that contain those 4 points, disks of the same radius that contain those 4 points, radius 2 epsilon. So can create d sub I disks of radius 2 epsilon, such that each d sub I contains zi, wi, zi plus 1, wi plus 1. So in the book, they draw them sort of centered. That's possible. Okay, zi, wi, zi plus 1, wi plus 1, wi plus 2, zi plus 2. Right. So you have di here, and you have di plus 1 here. Containing the next 4 points. Okay, everybody all right on the construction? Yeah, kind of.
So we know that if it's zi and zi plus 1, or maybe the other way around. One pair of points is less than or equal to 3 epsilon away, right? But how do we know we can fit all 4 in a disk of radius 2 epsilon?
Yeah, that's why I was being a bit careful about the construction here, right? So you take z sub I. Z sub I is going to be gamma s at some fixed time.
Yes.
Use that same time to create your wi.
Yeah.
Right.
Yeah.
By this fact,
They're within epsilon.
They're within epsilon. These guys are within epsilon. So this distance is epsilon, smaller than epsilon. Each of these distances is smaller than epsilon. From z sub I to wi from
Right.
z sub I.
Oh, I see. And zi to zi plus 1 is also less than.
Exactly.
But so does that mean we should center the ball at either zi or zi plus 1?
Yeah. So
Okay.
yeah.
Because if we do, yeah. Okay.
Yeah.
I see. I
Yeah.
understand. Thank you.
Yeah, so in the book, they've drawn it sort of centered at some sort of midpoint here, which will, I think, you can just slide it over to that point without affecting it.
Okay, cool. Thank you.
Yeah. Yeah. Okay. Other questions? Okay. Okay. So what's the point here? So now on each of these d sub I, let capital F sub I be a primitive for little f. Okay, so right, you got these disks, and you can take primitives. Your function is holomorphic there, so it's got a primitive. Okay. So so notice that they're both f sub I and f sub I plus 1 are both primitives of f on the intersection di, the intersection of the two disks, right? Right. So both of these guys are primitives for the same function there, and so they differ by a constant. Right. So f sub I and f sub I plus 1, this is constant on that intersection. Okay, and this is where we play the trick. Okay, so right, so you look at the point z sub I plus 1 and the points z sub I plus 1 and wi sub 1, I sub 1. Right, you know that f sub I plus 1, z sub I plus 1 minus f sub I plus 1, w I plus 1, I'm sorry. Sorry. You know that the difference between f sub I plus 1 and f sub I at this point must be the same as at the other point, right? Because this is a constant. Right? F sub I plus 1 wi plus 1 minus f sub I wi plus 1, right? And then change just flip things around a little, and you get f sub I plus 1, z sub I plus 1 minus f sub I plus 1, wi plus 1 equals f sub I, z sub I plus 1, minus f sub I, wi plus 1. Right? So I just interchange some things. Okay, so right, remember what we want to show, right? We want to show that the integral over gamma S1 equals the integral over gamma S2. Okay, and so what we do is we break gamma S1 and gamma S2 into subcurves, into a sum of curves. Okay, so let gamma S sub 1 super I from I equals 0 to n denote the part of gamma S1 from zi to zi plus 1. Okay, so we break it into pieces. Okay. Is gamma sub s sub S1 super 0, super 1, 2, 3, etc., etc. Okay, so okay, so now let's consider the integral over gamma S1. Well, that's going to be the sum of the integrals, over the parts from I equals 0 to n. Right? But on each of these parts, we have an antiderivative, right? Right. This is within. So this part lies within the ith disk, right? So we can use the fundamental theorem of calculus there, right? And we say, well, this is going to be just f sub I from the second point, z sub I plus 1, minus f sub I at the initial point, from I equals 0 to n. Right? And you do the same thing similarly for the other guy, right? Okay. So then, right, if you're looking at the difference, well, that's going to be right, summation f sub I zi plus 1 minus f sub I zi minus f sub I wi plus 1 minus f sub I wi. Right? Right. Right? Okay, now we pull out this thing, right? We pull out this observation about the differences. Right? We know that this thing here, right, so this is from I equals 0 to n, right? So we can swap this with the next antiderivative up, right? This is going to be fi plus 1 zi plus 1 minus fi plus 1 zi from I equals 0 to n. Whoops, what am I doing? This should not be a W. Wait. Sorry, I've got it. I messed up a little bit here. Sorry. This will be fi zi plus 1 minus fi wi plus 1, sorry, minus fi zi minus fi wi. That's okay. Right, and now we pull the trick here, right? So we can turn this thing into fi plus 1 z sub I plus 1 minus f sub I plus 1 wi plus 1. Right? Okay, and then what do we have there? We got a telescoping series, right? We have a telescoping series, and so we only end up with the top. We end up with the top term, fn plus 1 zn plus 1 minus fn plus 1 wn plus 1 minus the bottom guys, right? f0 z0 minus f0 w0, right? But z0 was alpha, z0 and w0 were the same point, and zn plus 1 and wn plus 1 were the same point, the terminal point, the initial point and the terminal point, and so we get 0. Okay. Yeah. Okay. So what does that tell you? That tells you that as long as you've got this homotopy, and as long as you choose guys that are within delta, whose s whose s variable is within delta of each other, then the integral over that path is the same. It doesn't change, right? And then so you just move little by little. You've got finitely many steps, and you go from gamma 0 to gamma 1, and the integrals are the same. Okay, that's it. Bye.